Okay, now I will try to be a little quicker this week without rushing through. What I will do is some of the slides that are pretty much out of the study book, I'll only pick one or two things out of it to discuss. But the beginning is actually really important, because if you don't get the concepts of this, it's a little more conceptual than metrology is. What happens is you lose track of where you're at. So really, if you lose track of where you're at, I actually expect you just to say stop, right? Okay? And we'll probably break this into like 40 minutes, if that makes sense, if we can try to do it in that time frame. So it's two aspects. It's monitoring and deformation, right? Now, deformation is for, hopefully surveyors don't cause deformation, right? You know what I mean? We're a very green group these days. When I started surveying, we chopped down every tree we could see. We don't do that anymore, right? It's the monitoring, obviously, is the surveying side that we're interested in. So the objectives of this particular module are fairly straightforward. Understanding dynamic and static, we'll come back to that, what the difference between those two are. The key elements in planning, absolutely critical, right? And more critical with this particular course because, as you've seen with some of the other modules that you've been doing, is that more than other courses you've done in the program, everything requires you planning. Look at assignment 2. I've read the forums on that with everyone going, I can't find a research paper that tells me how to do the answer. And, you know, Zara is quite correct in saying, well, because there isn't one. You know, that's the reason. So planning first, how to do problem formulation, we'll push that a fair bit. Critical success factors, right? I mean, you want to win. You know, in this area, it's actually, you can't afford to lose. And also, you are often dealing with things that are past your lifetime. So most dams of a certain size in Australia have a minimum of 50 years of monitoring. Bridges have the same. So if you've suddenly started your career tomorrow, right, you're going to be gaga in an old age home by the time they're still monitoring that bridge. So how you set it up and started it, that gets continued over the years, is important. And there's a little bit of stuff on the geotechnical side and structural monitoring instruments that you probably haven't covered before, and we will cover those because they are very common. There's you'll see them in place, and also because of the nature of you're involved with structural and civil engineers, right? Sometimes mechanical, is that if they don't know about the surveying side, well, that's their problem. But you should actually not look absolutely dumb when they say we're using a piezometer or, you know, a strain gauge or something similar. You should go, yeah, I know about them, right? You may as well look. You may not know a lot about them, but you may as well look bright to start with. And the last thing is have a look at the role of the surveyor. Now, one of these things, and I was talking about this earlier, was that the surveyor, too many students approach this and say, oh, I can't see myself ever monitoring a major dam, right? Can't see myself ever using a laser tracker, you know, in metrology. And then some surveyors, why are we doing hydrographic surveying? I'm never going to do that. I get seasick anyway, you know. You mean that type of thing? The reality is you are supposed to leave here as a professional surveyor, covering all aspects of surveying field. Maybe not in depth in some cases, but certainly all aspects. So if anyone asked you about any aspect of, you know, the spatial side of surveying, you should at least have some answer. It's a very important component of it. Okay, so deformation monitoring is, if we're monitoring and nothing's changing, well, that's actually good, right? But the reality, things do change. So it really is a systematic measurement, tracking, you know, making notes, documenting the whole thing of an object. Now, this object could be small, right? And it could be very large. So the reason to use it is there are usually stresses involved in these various large, particularly large constructions, right? And some of those stresses are hidden. Now, if you're following the news in Australia with all these high-rise unit buildings, you realise that there are problems with some construction and they can't necessarily be monitored. That one in Sydney, by the way, if you actually watch the news, you could see there were a bunch of surveyors using scanners and what looked like a laser tracker of some sort. They could see a laser beam. So they were actually measuring the outside of the building to see if there was any movement, right? Yeah, but shoddy building, I think was the... Yeah. Well, that happens a lot in, I've got a cousin who lives in Amsterdam, and she's just bought a house on the canal. Everyone has to share the cost because all the houses are moving. So the neighbours on this side have to share the cost for these neighbours to strengthen all the walls. But they're all tilted. I mean, you walk into the house and you're like this, you know, bending over. But it's one of those things that, yeah, building on poor land is a big issue. Okay, geodetic measurement. Now, don't take it in the traditional sense. Traditional geodesy is, you know, setting up a national network and everything else. Geodetic really means, in this case, using instrumentation and techniques at a high level, right? And these tools that we're using, you're pretty much should be familiar with. Maybe large-scale metrology. You're now experts in least squares adjustments, I presume. I have to question one of sign one. Perhaps that's going a bit far to say that, but you will know a lot more about it before the end of the course. So that's geodetic. You're on the geodetic side. Geotechnical is the monitoring without someone measuring externally, right? So they're specialist instruments. Some of them are actually buried inside walls. Quite commonly in dams and bridges and other things, they are physically inside the walls, right? Wivenhoe Dam has quite a number of them, you know, that just continually monitor by wire. The new techniques are now more going to wireless, Bluetooth, things like that. And we'll cover those in reasonably time or brief. There is some work on Ugandari, which that text is in the library. It's probably one of the more recent surveying texts, right? He's a professor in the US that has written a book on precision surveying. It's in parts really good, in parts it's a bit dated and a bit irrelevant, right? But it's worthwhile as a backup reference if you don't understand something, look at that. So he's coming out of his stuff. There's these things called causative effects, right? So they actually come from the model, the object itself, right? So if you put a big tower on the top of this building, it's going to be affected by wind, by sun, will expand if it's steel, right? Okay, that's a causative effect. The physical properties, because it's metal, it may rust. It will expand in temperature, right? Concrete in walls, even earth dams, the material changes. So they're the physical properties that could deform it, right? So you've got things like the response behavior of materials, other aspects, and how it's built. The geometry is fairly important. There's a reason why the pyramids are still there. Pretty good geometry, right? You know. Okay, and the response of the object in the form of deformation as output. This is a little bit like someone punching you, you know. I mean, when you're standing up and the wind's blowing on, they're all external influences, right? Your physical makeup is a causative internal thing. But if someone comes along and punches you, the reaction and the outcome, whether you're on the ground or not, right, is the response. So if you weigh, I don't know, 200 kilograms and you're 6'8", you know, and I punch you, probably you wouldn't even feel it. For number one, you just flick, right? But if you weigh practically nothing and you're small, you know, you get knocked around. Not with advocating punching anyone, just to test, but... Okay, so the types of things, and I'm going through this a little slower because I want you to actually have this terminology in your head as we go through. So static deformation, and I'm trying to use the example, this is a dam, right, a arch concrete dam. So the static deformation takes place generally over longer periods of time, right? Earth changes, you know, subsidence. So, you know, say you're saying the building built on basically marshland, right? It's not going to fall down in 3 weeks, but over time, the complete weight of the building. So you tend to have a periodic program of observations. The design of that program would be such that you actually could pick up whatever that is. Now, you saw with the tide gauge question in assignment 1, how you looked at over a fairly long period of time. You know, only actually 2 people actually got it right, the answer at the end. It was hidden a bit. It's actually the tide gauge is moving. So there's actually tectonic plate movement. So it's not that the satellite telemetry is getting better, which it is, but it's not just that. The reason it's converging is the tide gauge is physically moving, you know. And Zara's put a graph in, you'll see in the solution sheet that shows you the GNSS results from that. So it's quite interesting. But you see how often you have to have that long-term measurement to get a pattern. You know, when it says it's moving 1.2 millimetres a year, you know, you don't notice. That's where climate change and, you know, sea surface change is so critical. And in Zara's thesis, which she did in this area, you know, when you look at this pattern, you go over 30, 40, 50 years, and it hasn't altered. You know, the change is still there. It starts to add up significantly. So that's what we're looking at with structures, the same type of thing. Now, dynamic deformation, and if you take this lovely-looking bridge at the bottom, right, that's thin bridges like that have a sway. If you've ever driven across the Golden Gate Bridge, you can physically see the wires in an oscillation. You know, the main cables, they're big cables, admittedly, right? And you occasionally feel it even on bridges in Australia, some of our bigger bridges, you'll actually feel the bridge can move. It's meant to move, right? So the types of things would be temperature. You know, as things heat up one side and not the other, you get expansion. And particularly wind with buildings. They become you know, wind is a major factor with buildings, right? I mean, some of the very tall buildings in the world, and when in Module 9, when we cover high-rise, you'll see some features of how much these buildings move. Quite a bit, right? And they're designed to take care of it. So this is actually a harder area when you're talking about deformation and monitoring dynamic, because you don't actually know when it's going to happen. I mean, it might be blowing, right? But are you actually able to be on site to measure it? Or have you got the things on site to measure it? And is the equipment you use for this long term the same equipment you use for this? So there are differences between the two, but just keep on thinking static and dynamic. And the other part we need to think about is timing. So now we'll use this term epochs, which is sort of like the tide gauge stuff, right? What were the epochs in the tide gauge stuff? Most people put it down as years. You actually should have looked at if you calculated the decimals on the year, it's lunar months, like 29 days, right? So, which is logical, you know, so that's why they use the decimal, because it would change over the years, right? Yeah, so yeah, most people knew that it was obviously not a standard one. So epochs are what we're going to look at. And from a surveying term, and this isn't always the case, we tend to say that epoch 1, time 1, right, is the as constructed or thereabouts. So if you build a big dam or a big structure, often the surveyor has to come back and do an extensive as constructed as required by law, right? Now, when you're doing that as constructed, sometimes when they know that you're going to be monitoring that structure for a long period of time, there's a lot more effort put into the as constructed to actually go, that should form the base of future monitoring, because there's a fair bit of work involved, right? So they'll come back to that. Regular intervals, do you do regular intervals or irregular intervals? You'll see later on, for example, we're in a heavy drought period at the moment, right? Now, do we actually measure the big dams now? Because they're unloaded. Now, there's not a big water pressure on them. And then measure them when the dam's 80% full to see what the deformation is. Or do we go along and say, here's the contract, you have to come every 6 months, you know, every year and do these sets of measurements. Well, you might actually, you'll see later, I'll show you how you might end up with the wrong time period to measure. So looking at the structure itself, you could take from the geotechnical side and actually say, look, I expect that there's going to be no movement in this concrete, right, for 5 years. So we don't really have to worry about it too much in that first 5 years. And concrete, as developers know, hide a myriad of sins, right? The recent 2 years ago, the major bridge collapse in Italy, you know, a lot of people died. The one that actually fell down. It was on the news. It was big news. Right? Anyway, it was not that old a bridge. And now all those bridges of that type around the world are being checked. And in London, they've actually had to spend $100 million in one case of fixing it up. So they encased all the cables in concrete because that protects them from getting corroded. But when miniature leaks happened, no one could see it. And then actually these wires, and these wires are like 1,000 strand of small wires wired together, this thick, just started to unravel and just snapped. And then what they call single port of failure, once one of the wires went, the whole lot just went kaput. Very disastrous. Or incident-related times. Now, probably earthquake is something we don't do a lot here, right? I've been fortunate to live in countries that have a lot of earthquakes, and I'm very susceptible to them. I can feel them before other people do. You get that feeling. But flood is a particular one in here. That's when we load up. Our dams get loaded. Our culverts get loaded. Flooding into basements of buildings, right? You know, what's the deformation impact of that? So in Australia, floods and high winds are probably the key one, right? So don't worry about the detail here because it's in the study book. But generally, constructed hard material structures you should be aware of, things like dams, bridges, high-rise buildings, right? Soft material, also dams, earth dams, right? Groins, you know, like in the Gold Coast, we have a lot of groins coming out in the ocean, right? Dikes we don't see so much. It's mostly in Europe, which retains the water. Groins deflect the water, in the ocean particularly, and stabilising walls. Here we could add to that a large number of levee-type walls that we have on waterways. Earth movement, slope failure, earthquake, and bring into that earth movement into mines. Our mines are very big, our open cut mines, and it's a major cause of accidents. So what you need to do is to be able to monitor those critical slopes in mining. And tectonic movement to some extent in Australia, but in other countries a lot more. And then small scale deformation is things like cracking in concrete that may lead to something major. Okay, so you should have in the head this time there's, excuse me, dynamic monitoring, okay, static monitoring. You monitor at epochs, set times or random times or cyclical times, and now you want to come to actually the model. And this is very much like metrology, and it actually is very much something you should think in normal surveying. Go back to question 1 in the assignment. You had an object model. You had that piece of concrete in the middle of the subdivision or whatever it was, right? And you had a measurement model. You actually had 2 of them. You had one surrounding it, and then you had a greater one, which was the PSM, like the national control, right? They are models. And if you think in those terms, it helps you to actually think those problems, make the problem statement clearer when you're doing this sort of work. So the object model is usually the realm of engineers and other people, and the measurement model is certainly the realm of the surveyor. Now this large chart is in the book. It's just so you know it's in there. It's very pretty. It's got lots of colour, right? Except for those people who won't pay the money to print out in colour, you know. So what you're really looking at is you start with an object model. And let's just pick something, a bridge, right? So that's going to be designed. There'll be a whole lot of studies before it ever gets to being started. And then someone will do an object deformation model. How is that bridge going to move under static and dynamic pressures? Okay, we're bringing back that first part of the lecture. When you know that, you get a measurement model. So you actually can put down and say, and we usually use what they call FIM, finite analysis, right, for the model. And then you know what should move. In other words, we expect the bridge to sway in 100 km/h wind by so much. Yeah, in the middle, near the edges, up and down maybe, right? And in the long term, if there's subsidence of the ground, we would expect this would be the impact. So that's mostly the engineers would come into that. Then you go into internal monitoring. In other words, things like the gauges we'll talk about later on, stress gauges and piezometers and all sorts of things that will measure internal changes. And external monitoring, which tends to be the realm of the surveyor. Now, those two things aren't mutually exclusive. More and more often, and you'll see this in Module 9, when we talk about buildings, there's a thing called the building health that now is legislated, you must maintain for many years. Those building health is actually a combination of external and internal monitoring. So both those things you have data collection, right, and the combination of those, you end up with a deformation analysis. Now, what you've got to do here is different to what the surveying you've been taught or you physically do in the field, is that in the field you would go through much the same process. You would set out the road or the highway or whatever, right? Someone comes lost, put the black tar on the top and a few things on the side and the advertising signs up, right? And you're finished. You walk away. You know, do the as constructed. You go and, you know, go to the wherever, have a cup of coffee with your mates and boast about the highway you built by your own 2 hands, right? The difference with deformation modelling is this is just phase 1. So when you do the deformation analysis, you know, it's going to be for a long time. So then you may have to go back and go, Okay, we did that. It's actually moving 12 millimeters and not 5. You know, swaying. So then it has to go back to the beginning and go, was our object modeling incorrect? Right? Or worse perhaps is if you picked up no deformation. Okay, then you would go, well, why am I not seeing the expected movement? So the one on the right is how the study book has more detail, but try to keep that in your head of, you know, you start with an object, there's a model about that object, and then you go down through internal, external monitoring, right? You'll end up with an analysis of the results. That analysis may then mean you go back and change the game plan. Okay, just quickly, deterministic modelling, because most surveyors don't deal in this field, is trying to identify, if we've got a big concrete block, right, and you're going to have trucks driving over it all day, you know, in some form, what happens to the concrete block? So that's what structural engineers, mechanical engineers, civil engineers to a lesser extent, right, actually look at. Are there vectors of force? You know, and they use a whole lot of mathematical models. The one you'll hear about a lot is FEM, finite element methods. Now, it's quite complex, but it really gets down to going, if that's our block of concrete, you know, like a big block of something, at any point in there, what's likely to be the cause and the reaction to any force? So a 10-ton truck drives over it. What happens to all the finite elements, the face of the block, the underneath, the reactionary force back up on the truck, you know, that type of thing. And usually, like I said, carry out. Consult with surveyors is not unusual. So when you do the object model, right, you look for the critical elements of the structure for monitoring. Now, when you do those critical elements, you've got to go, can you actually monitor it? Like you might say, we'd love to monitor, you know, the inside the pylon of a dam, of a bridge, right? Well, if you can't get inside it, yeah, there's no use even considering that. You've got to monitor where you can. Plan monitoring points, lines and areas. Are you dealing in 2D or 3D space? You should understand this quite well, and we discussed this a bit in metrology, right? So 2D is what you tend to be, the plane is just the XY, basically. If Z comes into it, and most monitoring we're talking about 3D, but then, of course, you will end up with 4D in the end. Because monitoring, by its very nature, monitoring must equal time. So you're always adding your three-dimensional coordinates to a time factor. The uncertainty factors of the deformation. Now because you've been through 2301 where there was a reasonable introduction into errors, right? You've done Comps B, right, where you did least squares and other things. And some of the stuff you've done in this course, this particular course, you should be starting to understand that you should always know the uncertainty factors. Not just in the equipment you use, but also if a structural engineer says we expect this will expand by, you know, 4.5 millimeters, you know, over 3 years, you should be saying to them, what does that mean? Is that a 95% confidence level? Now, the reality is most engineers will say to you, oh, that's the tolerance. Now, that's something surveyors got to overcome. I think in Module 2 I spoke about that a fair bit. You know, the tolerance is actually not a statistical term. You know, so when you get a contract and the tolerance for the road surface, I think was the example I used, if you can remember back to all those weeks ago, right? You've got to interpret that. So at best, you should actually not only query it, but query it in writing, get it in writing, right? To say that the standard deviation is such and such at a certain confidence level. Because there's not much use them coming back to you saying, oh, we think it's 4.5 mil plus or minus 12. You know you're going to find it hard then to measure that because the random nature is quite large. Okay, as I said before, any of the deformation vectors normally is a function of time. Whether it's absolute or relative, another thing you should have more in your head nowadays, right? You know, I mean, does anyone really care if the whole dam moves? But you might care whether it's moved 2 millimeters across a critical point. So that's why crack analysis, you know, like in those apartments in Sydney, they were looking at what we thought were small cracks, but engineers were going, you know, there shouldn't be any cracking, you know, in this area, right? It's not a good idea. And planned redundancy. Another thing that should be getting into your head a lot. And this is one, I mean, you have to suffer under all this new technology you have to learn, right? But one of the nice things about a lot of the new technology is redundancy is not hard to do. You know, I mean, you see with a total station, you saw with question 1, right? Measure another, you know, direction and distance. You actually have to lift your hand. Well, actually, you don't have to do that. You could time it. But you probably have voice recognition, and it'll actually measure again for you. So it's not actually as complex as it used to be. And critically, and we'll have some pressure on this, is monumentation. When you build that highway, you know, and you're doing the surveying for it, it might take a year, right? By the time you start from the beginning to end, and you're going, oh, look, I might put some things deep driven into the ground, some recovery marks, because I might have to come back if, you know, a bulldozer drives over it or whatever, right? When you're doing a lot of monitoring, you're saying someone in 50 years' time, you know, they don't even attend lectures. They don't even have online. They have, you buy it, instead of hex, you buy an embedded surveying chip that goes in your head, right? And you pay $45,000 for it. You know, and you go to hospital for a few weeks and then you come out a surveyor. Who knows what's going to happen? But monumentation is you've got to think so far in advance that the monumentation becomes far more important than probably any of the monumentation you've been doing in surveying, because it's now becomes a time element, a duration element. And what are the critical failure indicators? That sounds like the last thing on it, but the reality is important, because, you know, if Wivenhoe Dam is moving, right, at which point do we actually move all the people away? You know, what is the critical failure point? And that's something for engineers or anyone, it's very, very difficult to predict. Okay, this is in the book. I just want you to look at two things. This comes out of the US Corps of Engineers. It's an odd thing in the US is that the Army actually is in control of most of the dams in the US. So that includes the surveying, the engineering, monitoring, the whole lot. And have been, you know, so if you ever look for anything, it's quite a good resource for lots of surveying, the US Corps of Engineers. They do a lot of stuff, right? So you see these sorts of things like a dam or structure, they're talking about 5 to 10 millimeters, right? I would think these are probably going down a bit. Vertical, suddenly you're going 0.2, relative 0.2. We're starting to get to fairly high accuracies, and that's partially because that sinking and subsidence is a critical part of structures, right? So if it is subsiding, you want to know. And don't forget, when they build these structures, you know, there's a lot of underground structural integrity put into it. So they really want to know if the thing's moving. So that's in the book. It just gives you magnitudes. So the measurement model, and this is the bit you do, right? You can assume to some extent the object model will satisfy the location of the points to be monitored, right? The uncertainties and everything else is given to you. Now, don't actually assume that all the time. One of the problems in question 1, and not too many students this year queried it, last year they did, far more vocal group last year on campus. They said, this is ridiculous. And we used airport as an example, the new runway at Brisbane Airport. And they said, oh no, because you're not telling me what I have to do. Right? And a few students were quite vocal about it, you know. They weren't quite as, a little bit more radical last year. They're the 4th years this year, so watch out for them. When they did that, part of the problem was that they thought that you are always going to get presented with a problem that's in clear surveying terms. So the assignment last year, similar to this year's, right, was actually written by the chief engineer who's doing the earthworks at the airport. Now, he's not a surveyor. He's going to kill you in terms of ground movement and compaction and things like that, right? So when he writes that stuff, it's very vague. Actually, it's vaguer than we actually put it down. You are the one who has to interpret that. You've got to be the professional and go, okay, you want this, you know, like in that thing of plus or minus 10 millimeters to the other buildings. You know, you should query that and go, well, what, all the other buildings or the ones that are just nearby? Like there's a building at the end of the runway here and there's one, you know, most runways are 3,000 meters, right? 3,000 meters away, 3 kilometers away. Do you actually want 10 millimeters between those? Or is it only around the hangars? You know, like that type of thing. You can ask those questions. And that's why I put on the bottom is that that's what's supposed to happen. In reality, engineers don't understand to the level of surveying things like constraints, geometric optimization is an area, right? Equipment capacities. They think you just buy a total station. You know, you go on Gumtree and just get one, you know. I mean, they don't understand there's a whole lot of varieties there. The climate, because, you know, climate affects our measurement, you know, the surrounds of it. And so the sooner the surveyor gets involved, and if you're in a position where you are coming up with a complex problem, try to get involved and volunteer to be in those discussions before you even have to come to the measurement model. Otherwise, it's a bit late when you start asking questions and saying, well, you want that monitored, but how are we supposed to set up on the water in the dam? You know, if you can say that early on, saying we can't see those points, you're not going to have line of sight, right? It's no use putting a GPS there because, or a GNSS, because access to it, you know, and the downloading from it is not close enough to control, or a cause station or whatever, right? So get involved as soon as you can. So the two broad categories, geodetic techniques, this is the stuff you've been doing, right? So there's total station, GNSS, precise leveling, right? Okay. I guess you could consider them traditional methods, right? And they tend to be contact. You physically do something that has contact with the object. It might be a laser beam that's got contact, but it is contact, right? So, and then you have the remote methods. So now this is like a scanner, and sometimes you'll have both of them operating at once. There's a lot of new scanners are total stations as well, or vice versa. Multispectral imagery, you include in that UAVs, right, which have getting a greater capacity of multispectral imagery, and non-contact, any non-contact aspect, right? So photogrammetry, like you did in the last course, you can consider that as well. So the key aspect of the surveying measurement model is the coordination framework, the thing that goes around it. Yep. Go back to question one. That's a simple, very simple question, that one, right? That's what you should be looking at in that coordination framework. The expected deformation thresholds. We're talking about an object. How is it supposed to move? What you were talking about was a model for the construction. How is it supposed to move? Accuracy and precision requirements. Now we mentioned that it was prefab, you know, the material, right? So when you're talking about that, you go, well, okay, it's prefab. What's critical there? The critical thing is that you know what it's prefabricated to. So that building was, I think it was 50 meters long, right? Say there were three beams, right, of about 16 or 17 meters each. I mean, do you ask the question and say, well, what's the prefabrication precision? You know? Now, some of you picked up in that particular area that the actual diagonals were important, right? Because particularly when you prefab, anyone who's built a garden shed at home even knows that the thing you measure all the time is the diagonals, because it doesn't like being out of square. It doesn't fit, right? So that's the types of things. The survey error budget. Now, is this term you would have, I think, in module 1 or 2? The term error budget rings a bell with you. You should be able to remember that. It's like a budget. In other words, what do you got to play with? You know, it's like when you go away for the weekend and, you know, and you're trying to impress somebody. You think, oh, this is going to be a problem because I've only got a $25 budget, you know. Well, that's what you got to work with the error budget as well. So your error budget includes not just the deformation, it also includes your equipment. And you don't want to be going and buying a TM30 or something that you know at $120,000 because it'll improve your error budget. You're going to be far more popular with your boss if you can use your existing gear and get the same results, right? Which, if you impress your boss, you get a rise and everything goes better. The network geometry. Now, you should be starting to see why pre-analysis is so important, because it allows you to play with the network geometry, right? I mean, some of you actually found pre-analysis was a bit of fun, right? Because you can move things around. I wouldn't say it's a lot of fun, but a bit of fun we could probably live with. And monumentation and recovery. Is this something probably those who have a lot of field training would actually be more familiar with, right? But it's something that students, it's a little bit jelly-like, you know, because you actually haven't had to build monuments. You know, and there is an art to that. If you go on to the, I think I've got some in the study book, the US Corps of Engineers, they've got like 30 pages just covering the type of monuments that you should be building. It's including material, how you test them, things like that. You let them settle. Okay, so network pre-analysis. Everybody here and online should be absolutely experts in this by now, right? Measurement reliability, that comes from the both that pre-analysis and also your understanding of the instrumentation you're using. Instrument calibration. Hopefully you understand from Module 2 this year that going along and just calibrating your instrument on the government baseline, right, which is called a Regulation 13, I think, right? Just doing that actually is for cadastral standards. It will give you a report, but you need to actually understand that calibration well enough to go, I'm not setting out blocks of land, I'm going to be testing down to 0.5 millimetre on a bridge. Can my equipment do that, right? So calibration is beyond just going, let's go to a calibration range. Documentation and data presentation, that will usually be a little bit prescribed if you're doing large structures. If you're doing something for the Toowoomba City Council or Roma, right, they probably won't have a pro forma. You have to write a report. Best way is to look at what other people have done. You know, identification of systematic and gross errors. We thump this because systematic errors make things go wrong. Gross errors make you look like an idiot, right? And trying to keep USQ's premier reputation as a surveying course, we actually don't want you to look like an idiot. You know, we don't really care about you, but we don't want you to look like an idiot because it reflects on the course, right? Gross errors, I can never say enough. Stick it in your head to actually think about it and think laterally about systematic errors, right? Just think how they can happen. Presume the worst. Okay, measurement, adjustment and analysis. We'll come back to this because you did a bit of this in Comps B, but you did mostly just straight mathematical solutions, right? And you've done the pre-analysis and you don't really have other questions at the moment coming up to do that. But we will discuss a little bit about when you're really doing an analysis. Most of you with StarNet, and we use StarNet because it's pretty typical of a least squares program, right? You know, if you do get bored over the holidays, you can always find some data and run it through StarNet and see what a real analysis is like. And of course, research, which is a lot easier now with the internet. Now, I can put a plug in here. When you research, you don't have to look up Wikipedia. And those you'll see on the assignment, Wikipedia is not an acceptable reference at all, right? You can go to Wikipedia. You can find material, and you might find the source of that material, but you should go to the source of that material to verify it, right? You can't put down Wikipedia as a reference. It's a real no-no. And fit for purpose, I think that's explained in Module 2 as well. Some of this terminology, I know it sounds very basic, but you'll be surprised in the profession, some of these things are relatively new terminologies to be used. Okay, I'm just going to finish the complexity of control and then we'll have a break. Those people online, of course, it's easy because they can just stop after 5 minutes and say, I've had enough of this. You guys have got no choice here. Okay, so some pretty pictures to end with. This is the Vidu Barrage dam in Romania, right? And it's a big dam. So that's why, if you can see here, I've tried to point out, that's actually a 10 to 15 ton truck. That little bit just there, right? So it gives you some idea of the dam. I want you to see this because you probably, and a lot of surveyors have never been involved with this sort of thing. When you go out and say, oh yeah, we can monitor the dam, when you get to some of these big dams and big other structures, right, the immensity, the size of it. So here you actually see these lines are actually control points for monitoring the dam in this particular case study, right? And this is the, let me get rid of this. Does this have an eraser on it? No, you got to go to the, that's irritating. There should be a eraser on the pen. Where's it? Oh, we'll leave it on. Won't do it now. Okay, this is the Katsi Dam in Lesotho, right? Do you know where Lesotho is? What a good question you ask. It's a little kingdom in the middle of South Africa, right? It's one of the most beautiful places you'll ever see. I've spent a fair bit of time there. I actually did part of the initial survey for this dam. Doing the levelling, when they're trying to determine the water and things like that. And this is at about, I think, 9,000 feet up. and it goes up to 15,000 feet, and one of the great car races of the world is held, called the Roof of Africa, which I've actually driven it twice, right? And it has a very high attrition rate. It's like 20% of the vehicles finish. Part of the reason is a little bit easier with newer cars, but you actually had to change your jets on your carburetor, because when you get up to 16,000 feet, the air's different, right? And the roads, as you can probably see, are, even here, they're pretty windy, right? But it's a beautiful country. Obviously, this was taken when it was nice and lush, right? And it's quite a big dam. So that crest across here, across the top, is 700 meters, give or take, right? So it's quite large. And it's pretty typical of a dam in that sort of area where you put dams in valleys, which makes them pretty hard to monitor, because they're very steep. So it's a lovely place. If you ever there's not many tourists go to Lesotho, right? So it's one of those places, if you can get work there, because actually they do a lot of surveying work. It's got diamond mines. That's its big thing. And people wear big hats. So, but it's a very friendly place, and it's been an independent kingdom for a long, long time, independent of South Africa. Now, that particular dam don't try to get the detail of this. This is well documented, and you'll see this slideshow if you actually just go on SlideShare or something and do a search, but I think it's on the resources on the study desk. A person has actually done quite a good slideshow on how this is all done. So this has some of the older techniques and a lot of the newer. So all these channels, inside it, hanging pendulums, hanging brackets. You can see a bracket up here on looking at the top left with a double theodolite on it, a double barrel theodolite. Pendulums hanging everywhere that are measured regularly. Because this at this time was built, a lot of the internal geotechnical data, it was expensive to do. It's getting cheaper now. So that was the internal side. And of course, little things that surveyors should notice is that it's difficult because you are dealing in small spaces, even setting up an instrument, very poor light, right? And also, when you remember, this is, I think, 300 meters or whatever, right? Or 260 meters high, is that you start here and walk all the way down, it can take you most of the day to get down there, and then you work for 10 minutes, you got to walk back up again. So there's a whole lot of other factors outside of just the accuracy. Now, so this actually, I won't go through this here, it's only a few minutes. I think this is on the study desk. It's a short video on the Katsi Dam, right? Okay, yeah, we might just have a break here for a second.